Hello everyone, my name is Yu. I come from Worcester Polytechnic Institute. Today I'm going to talk about our work on distributed attack reporting to solve the distributed denial of service attack and how to incentivize people to deploy our system. According to some statistics, there are more than 82% of the households subscribe to internet service in USA. There are more than 442 million smart home devices connected to the internet by 2020. However, home networks are usually lack of protection. For one, there is no security experts in home network to maintain the security. For two, home networks are not like enterprise where has been deployed a powerful firewall to protect the network. Based on this information, the devices in home networks are vulnerable to attackers to be compromised, and they can be easily controlled to join some botnet and launch distributed denial of service towards some other targets. So based on the huge number of the devices, the attack volume can be larger and larger, and they can be easily to fill the last mile bottleneck of a victim. Some other previous work proposed to stop attack at the origins, which could be very effective, but their method requires to modify the internet service provider's infrastructure. So which we believe is why this technology is hard to deploy. We proposed a method based on software-defined network architecture. It allows the networks to work with each other in the way that a victim can report the unwanted traffic to some other networks, and the other networks can stop the attack for the victim. We believe our method can incentivize the users and the third-party security service providers to deploy our system. Before introducing our method, here are some related work. Distributed denial of service attack is well studied by the committee. Some of them propose to use statistic and mathematical methods to distinguish the malicious traffic from the others. And they apply their method on some global network dataset, which is collected by the ISP. And some other researchers found that the distribution of attack origins can follow some patterns. For example, they can be symmetric and they can be neighborhood. To prevent the DDoS attack, for the CPU or memory targeted type of attack, they can simply install the filters to drop the malicious traffic. But for the bandwidth targeted attack, they just expand the bandwidth. We don't think this method is effective because the attack volume in the future is hard to predict, and it is very expensive to the victim. Here is a previous work, we call it AITF. It proposes a method to stop attack from the origins. When a victim receives some unwanted traffic, it reports the attack to the victim gateway, which is run by the ISP. And then the victim gateway installs a temporary filter to stop the attack for now. And then the victim is not going to see the attack traffic anymore. And after that, the victim gateway look for the attacker gateway and ask, hey, can you help me to stop the attack? The attacker gateway says yes, and then it installs a long-term filter at the origins of the attacker. Then it confirms with the victim gateway and say, hey, I already stopped the attack. And the victim gateway removes the temporary filter to save its table space. From this point, the attacker's traffic is stopped at the origin. This method is very effective to stop the distributed denial of service attack, but we believe it's hard to deploy because we need to modify the ISP's infrastructure. We propose a software-defined network architecture, and here is a system showed by the diagram. On your left-hand side, there is a home network, which means there is a device compromised and controlled by attacker inside this network. This network is enabled with OpenFlow protocol. So the PON router is actually a programmable router and connected with a remote controller, which is running in the cloud. And the PON controller is operated by some third-party security service providers. On your right-hand side, there is a victim network. It is also enabled with OpenFlow protocol and connected with another controller running in the cloud. And as you can see, there is a bandwidth bottleneck. So that means the victim network owner subscribed some internet service from the ISP. And this bottleneck is actually the downstream bandwidth limitation. There are some other PON networks out there, and all of the PON networks are trying to send trash traffic to the victim network and fill up the bandwidth bottleneck. The goal of our system is to let the victim network to report and stop the attack as quick as possible. Device owners in our system usually trust their third-party security service providers who runs the SDN service for them. But different home networks can subscribe the service from different third-party service providers. And different service providers usually do not trust each other. For example, from the PON network perspective, it cannot trust any people who send a filter request. From the victim networks, it cannot trust any people who send a filter is already installed message to him. And also, we believe our system itself is not going to be compromised. That is to say, the controller and the modified router and the cookies we are going to use in our system are not going to be compromised. There are some challenges we need to solve in our system. First, we need a way to know who is going to do the filtering. How can we know if the filter is installed remotely? What kind of information we need to send around? How can we make sure the person who sends the information is the right person who sent the message? Now we are going through the system part by part. When the PON device sends out a packet, it reaches out a PON router. The router elevates the packet as a packet in to the PON controller. When the controller receives the packet, it generates a source cookie for this specific flow. Then it inserts the source cookie to the packet as a TCP option. It sends the packet out to the router. Simultaneously, it creates a flow mod and pushes it to the PON router. And after that, the later packet of this specific flow is not going to be necessarily elevated to a PON controller. When the PON router receives the packet out, it extracts the source cookie and stores it in its local database associated with this flow information. After that, the PON router sends out the packet with the source cookie to the target. When the packet arrives at the victim network, the victim router extracts the source cookie and stores it in a local database associated with the flow information. And after that, it allows the packet to reach out to the victim machine. At some point of time, the victim router detects some attack traffic. The first thing it does is to stop the attack locally by installing some local filter. Secondly, it reports the attack to the victim controller associated with the source cookie it stored before. When the victim controller receives the attack report, it crafts a UDP packet to look for the PON network. Other than the source cookie it received from the victim router, it generates another destination cookie and append it to the UDP packet and sends the packet out. When the PON network receives the UDP packet, the PON router firstly verifies the source cookie, and it elevates the report to the PON controller as long as it's valid cookie. By doing this, any invalid attack report will be dropped at the PON router. When the PON controller receives the UDP packet elevated from the PON router, it pushes a flow mod to the PON router to stop the attack from the PON network. After that, it sends another message to the victim controller and with the destination cookie. The victim controller trusts this message as long as the destination cookie is valid. If it's valid, it pushes the flow mod to the victim router to remove the temporary uh, filter installed before. For now, the victim machine is not going to see the attack traffic anymore, and the filter is installed at the origin of the attack. We believe our method can incentivize both users and the third-party security service providers to deploy our system. For the residential network users, they can get notifications from the security service providers once their device is compromised. The other thing is we can save the home network bandwidth for them because when an attack happens, it usually uses up the upstream network bandwidth, which is usually very limited. And of course, we can protect the home networks themselves from DDoS attack. From the perspective of security service providers, the big thing is they can make more money. This is because they can provide more meaningful feedback to the users because they have a global view of the attack origins, which should be important information for them to diagnose and analyze on the attack activities. We have deployed our system in a lab environment to evaluate the performance. We deployed three physical routers for Pwn router, ISP, and victim router, respectively. Each of the routers are flashed with OpenWRT and installed with Open vSwitch. We have two VMs running two of our controllers on a local laptop. And we have 5 attackers for simulation. Each of the attacker has 2 Mbps attack traffic, which is for the simulation of the upstream bandwidth limitation. So on the ISP router, we are able to see 10 Mbps attack traffic. For the network, for the victim network, it subscribes 5 Mbps downstream bandwidth. So as you can see, we can easily fill up the last mile bandwidth bottleneck. This diagram shows our experimental result. At around time 1.5 seconds from the green line, you can observe the attack is launched by the Pwn device and the attack volume is around 10 Mbps. From the Pwn network interface on the ISP router, it observes the attack traffic fluctuates around 10 Mbps as well, which is shown by the blue line. However, from the green line, you can see there is a 5 Mbps attack traffic observed by the ISP router. This is because the victim network subscribed 5 Mbps downstream bandwidth. And at around time 5.5 seconds, you can see the blue line drops very soon. This is because there is a filter installed on the Pwn network, which is close to the origin of the attack. And at around time 6 seconds, you can see the green line drops as well. So there is a time difference from here to there. This is because the ISP queued some packets on the router. So from the victim's point of view, you can see the attack traffic from the very beginning of the attack. But after a short while, the attack is appeased. This is because the victim reported the attack to the victim router, and the victim router installed a temporary filter locally to stop the attack. We also evaluated the overhead of our system. So we measured the round trip time from the Pwn device to the victim device, and the green line shows the result without running our method, but only run with idle SDN architecture. The blue line shows the result with running our method. So as you can see, the OR method doesn't add too much overhead compared with an idle SDN architecture. And but overall, or with all methods running, there are more than 80% packets have less than 60 milliseconds round-trip time, and we believe this is not likely to be perceived by the users. To conclude our work, we developed our SDN-based system based on previous work to stop attack from origins. It can release the burden on victim side and save bandwidth for victim. It incentivizes users to deploy because they can understand more about their network and have better network environment. Security service providers can aggregate more information for analysis and provide better service to users and make more profit. We also evaluated our method and showed that the overhead is acceptable to users. That's it for my presentation. Do you have any questions?